All right, so this is 4.3 part 2 for business calculus, and we're going to continue on finding derivatives of logarithmic and exponential functions. All right, so the slide that we left off on has the derivatives of the ln of x, the ln of a function, e to the x, and e to a function. All right, and again, remember these bottom two are chain rules. All right, so let's keep doing some more examples. So let's combine a logarithm and an exponential. So we're going to find the derivative of ln of 1 plus e to the x. So we take the derivative with respect to x of ln of 1 plus e to the x. Remember that for the derivative, this is the outside function is ln. Okay, so that's what we're going to tackle first. Then e to the x is inside that outside function, so we'll tackle that in the chain rule. So remember the derivative of an ln is 1 over the stuff. And then we're going to multiply by the derivative, or we're going to put the derivative of the inside on top of that fraction. So the derivative of 1 is 0, and the derivative of e to the x is e to the x. We can't do anything else with that, so we just stop there. These are pretty straightforward. Don't overthink them, and don't try to do more work than you have to do. Okay, so be very methodical about it, and take it one step at a time. All right, so what if we have something of the form e to the kx? So like, I want the derivative with respect to x of e to the 5x. Okay? Well, we can take several steps just like we know. It's e to the 5x, and then the derivative of 5x is 5, and then I could rewrite it as 5e to the 5x. Well, this happens every single time, okay? Anytime that constant that's in the exponent ends up out front. So what we can have is just a rule that you can remember. The derivative with respect to x of e to the kx is equal to k e to the kx. And this works for any constant, no matter what. All right, so this is just another rule you can remember. If you don't, it's not a big deal. This didn't take us very long. We just had one middle step. But if you do remember it, you can go from here all the way to the end in one step. All right, let's keep going. So, derivatives of exponential functions. These differentiation formulas enable us to find instantaneous rates of change of logarithmic and exponential functions, just like we found instantaneous rate of change of all the functions that we found derivatives of. This doesn't change. In many applications, the variable stands for time, so we use t instead of x, just because a lot of times with these exponentials and logarithmic functions, our variable is dealing with time. All right, so let's look at example 9. After t weeks of practice, a pole vaulter can vault h of t equals 15 minus 11 e to the negative 0.1 t feet. Find the rate of change of the athlete's jump after 0 weeks, which is at the very beginning of training, and then again after 12 weeks. So if we're finding rate of change, okay, just like in other sections when we're dealing with derivatives, that rate of change, find the rate of change is your hint that you have to find the derivative. Okay, so I have the derivative, or h prime of t. We're going to have the derivative of 15 is just 0. And then I have negative 11 times negative 0.1 e to the negative 0.1 t. For all of this part, I'm using the slide we just looked at, that e to the kt derivative. Okay? When we simplify this, we end up with 1.1 e to the negative 0.1 t. So to find the rate of change, you can't just put in the numbers first. You have to find the derivative first, then go put in the numbers that you're looking for. So for part A, if I want h prime of 0, so what's his rate of change at 0 weeks? We plug it all in. We have 1.1 times e to the negative 0.1 times 0. Well, anything to the 0 power, which is what this would be here. Anything to the 0 power is 1. So 1 times 1.1 is 1.1 feet. So when he's first starting to try, that rate of change, each day he's growing, he has a rate of change when he first starts of 1.1 feet. Okay? So each week he's being able to pole vault more 1.1 feet. So let's see what happens at week 12. What's that rate of change at week 12? So same concept, we're going to plug 12 into the function. 1.1 times e to the negative 0.1 times 12. When you plug this in, we get about 0.33. And you can plug all of this into your calculator right here. You don't have to do it in several steps. Although I do recommend plugging the e part in first and then multiplying by 1.1, but it really doesn't matter either way. As long as in your calculator, that entire exponent is in a parenthesis. So back to the problem. We get to 0.33 feet. So at 12 weeks, each week at 12 weeks, he's only able to gain 0.33 of a foot, or about a third of a foot, in his pole vaulting, as far as he can go further. Well, what does that mean? If you look at the next slide, there it goes. This result is typical of learning a new skill. Early improvement is rapid. Okay, when you first learn, you're gaining knowledge very, very quickly, but later improvement is slower. This trend is called diminishing returns and may be seen in the leveling off of a pole vaulter height in the graphs below. So at first he's coming out fast. He's learning how to pole vault higher heights very quickly, and then at some point he's going to level off and he's going to hit the max of what he can pole vault. All right, so this is that leveling off, or that point of diminishing returns where things level off and don't gain traction as fast. Okay? So, the last thing we want to look at is maximizing consumer expenditure. So the amount of a commodity that consumers will buy depends on the price of the commodity. All right? For a commodity whose price is P, let the consumer demand be the function D of P. And if you multiply the number of units D of P by the price, gives the total consumer expenditure for a commodity. All right, so D of P is our consumer demand at a given price. All right, and then we have the function E of P is equal to P times D of P, and that's your consumer expenditure. Or how much is that? How much are people going to buy? So if consumer demand for a commodity is D of P equal to 10,000 e to the negative 0.02 p units per week, where P is the selling price, we want to find the price that maximizes consumer expenditure. Okay, go back a couple sections and recall from chapter 3. Maximizing or minimizing a function is taking the derivative. Okay, so we've got E of P equal to P times D of p. So for this function, I have p times 10,000 e to the negative 0.02 p. You could leave a function exactly like this and then do the product rule. I'm going to go ahead and rewrite it just for me. And we have 10,000 p e to the negative 0.02 p. All right, what I want you to do, I want you to pause the video and take the derivative. If we're going to maximize this function, we have to take that derivative. So take the derivative and come back and check your answer. Okay, sorry, I had a mess up in my video. All right, so when you take that derivative, what you should have ended up with is 10,000 e to the negative 0.02 p minus 200 p e to the negative 0.02 p. And then again, to find that maximum value, we've got to set it equal to 0. In order to set this equal to 0, I've got to factor out the common factor. When you do that, you can factor out a 200 e to the negative 0.02 p. And what will be left is 50 minus p equal to 0. When you do this, the very first part of this, the 200 e to the negative 0.02 p, will not ever equal 0. So we only have to deal with the second part. So 50 minus p equal to 0 gives us p equal to 50. Now they asked for the price that's going to maximize that value. In order to prove that you have a maximum value, you have to take the second derivative and plug your value in. Okay, so we're going to prove this by taking that second derivative. So what I want you to do is pause the video again, and we're going to take the second derivative, and you can actually start from this factored out step, and it would make it a little bit easier, or you could factor from your original. Wouldn't matter. I'm going to start from this factored step. Okay, so pause the video and let's take the second derivative and prove that we do have a maximum. All right, so if you take that second derivative, what you end up with is negative 4e to the negative 0.02 from a p times 50 minus p minus 200 e to the negative 0.02 p. If you plug in 50 into all of that for all the different p's, and I need another 50 right here. Sorry about that. The very first term turns to 0 because of the 50 minus 50, that's 0. This second term, the negative 200 e to the negative 0.02 times 50 becomes negative 200 times e to the 1, okay? Everything right here becomes 1. Well, a negative 200 times a positive e is negative, okay? So this means this is less than 0, showing that price or consumer expenditure is maximized at p equal to 50. All right, it's the exact same thing. That hint, maximize whatever, minimize whatever, that tells you you've got to take that derivative and find the critical number. It's the same thing as all the rest of the functions that we've dealt with. All right, that's the end of section 4.3.